in a quite specific scientific task devoted to time series forecasting in the domain of space level prediction. No, it doesn't work. Okay. Next one.
Вы можете скроллом вперед-назад.
First, a few words about the zoning domain. It is quite well known that the magnetic field of Vadim prevents us from the flow of charged particles of the sun, which is named solar wind, and due to presence of the Earth's magnetosphere, the light on our planet has such form as below. But the study of magnetosphere states and also the prediction of the state of the Earth's magnetosphere has significant interest from fundamental, from practical points of view, from fundamental point of view. Scientists wanted to verify the role of various physical processes information of geomagnetic disturbance. And from practical point of view, research is connected with the fact that strong geomagnetic disturbances, which we usually call magnetic storms, may cause disruptions in the radio communications, induce strong currents in white lines or power lines and electrical networks, harm railway automation, and also the spacecraft on near Earth orbits may be damaged by the flux of relativistic electrons on the orbit, which may increase the duration of strong magnetic storms. TV wants to tell us that magnetic storms are very harmful also for people health, but at this point there are no good facts which may either confirm this hypothesis or reject it. Possibly it may also. So the physical statement of the problem is prediction of a special geomagnetic index, which is called DST index, disturbance storm time. This slide presents some information about how this index is calculated. For us, it will be interesting that it is an hourly average of the disturbance of the magnetic field, derived from the measurements of magnetic field on 4 low latitude magnetic observatories, which are listed here. Such measurements are performed since 1957 and are provided for mankind for a special space geomagnetic information center in Japan. This is some more information about the DST index. We can see that this is an example of just the timeline of the DST index during September of this year. These volumes of the values of the index denote magnetic storms. The scale is in nanotesla, and the magnetic disturbances stronger than 550 nanotesla are also considered to be magnetic storms. Now we are on the phase of solar cycle when the number of magnetic storms increase. So the index forecasting is an important problem, and it is hard to solve. So machine learning methods are one of ways out to predict such kind of concepts. It's interesting that sometimes the magnetic storms cause also what we call in Russian северное сияние, auroras, and in September there was a strange magnetic storm when we had auroras in quite low latitudes, even in Moscow and in Minsk, some auroras could be seen, which happens quite rarely. I was thinking from the computation experiment on the index forecasting. The input data for machine learning models are the physical values that may affect the speed of the magnetosphere. First of all, these are parameters of the solar wind, solar wind velocity, proton density, and solar wind temperature. Then the characteristics of the interplanetary magnetic field, components with special coordinate system, and also the model of the magnetic field. This is itself, and also some characteristics describing the phase of the Earth's rotation around the Sun and around itself. It's interesting that solar wind and magnetic interplanetary magnetic fields characteristics are measured at a special point, Lagrange point, in the Sun-Earth system, where the mankind now has several spacecraft which measure the required parameters. Three of these spacecraft are American, launched from 70s of 20th century till 2015, the last apparatus. And now we're going to have the fourth apparatus launched by India. It is now on its way to this point. It's interesting that the point is situated between the Sun and the Earth. This is the point of gravitational equilibrium. So we have some advantage because the measurement is made quite far from the Earth. And about 40 minutes is the time of the way of solar wind from Lagrange point to the Earth. So it allows us to make the predictions. Now, to account for the dynamics of the changes, we need to take into account the history of these physical values. In our studies, we use delay embedding. That means that each parameter, except for the time characteristics, is described not only by its current value, but also by 24 historical values for velocity. However, when we perform the delay embedding, the dimensionality of the data, the input dimensionality grows several folds. In fact, here we have only 8 physical values, but when we perform delay embedding, it is multiplied by 25 powers. In total, we have 200 plus features, which is quite many. So there arises the problem of reduction of the dimensionality of the data. The problem is quite common for machine learning in general, but here we have some specificity of the data connected with the fact of delay embedding. Really, the adjacent delays were similar information. So possibly our data array has the property of the so-called multicollinearity. Yes, we need to reduce the dimensionality, but also it would be better to take into account this property. example, want to take the adjacent delays or to take several of them at some distance. It would be interesting to make this selection not by manual selection, but by some special order. So, yes, this is the list of the properties of the neural network we use in these experiments. Quite a common architecture. Nothing very interesting here. More interesting is the feature selection. As I said, the problem is quite complex. It may require a more complex architecture than just one hidden layer with 32 units. But we know that the more complex is the architecture, the larger, the greater is the number of waves that we need within this architecture. And it may be too high for the available number of patterns. Especially, we should take into account that some inputs may bear similar information, so some physical features also may be insignificant for the solved problem. Summarizing, there is a need for a special feature selection algorithm capable of dealing with feature multicollinearity. For the last 2 years, we are working over such algorithm and testing it on various problems, machine learning problems. So now I'll tell you the results on the described problem of time series. This is the algorithm itself. It's quite simple. We have the initial feature set, and then we select the feature which has the highest relevance in relation to the target variable. Now, to take into account the multicollinearity, we remove features whose similarity with the feature already selected is higher than some threshold value. We repeat it until the stopping criterion is satisfied. The stopping criterion may be either selection of a predefined number of the most significant features, or, for example, we may set a special XY threshold that limits the lowest relevance of the feature in relation to the target variable. So, in fact, we have 2 parameters, and also the terms relevance and similarity may mean different depending on a specific measure of relevance and similarity. And in this study, we took the simplest one, just Pearson correlation coefficient. We determine relevance and similarity in terms of correlation coefficient. Of course, other measures may be used instead. They may be different for these 2 types of threshold. By now, we tested, besides cross correlation, we also tested cross entropy for another program. But surprisingly, the results that we are seeing were not much better than the correlation. So I will present this result. Here, the work is being mentioned. And here are the results for this specific problem. This heat map displays the correlations of input features. Here we on the left we have the list of input features. The DST index itself, the magnetic field, the components, and the model, and the parameters of the solar wave. My time is yes. Okay. And the various lines depict various delays. We see that aside the highest outer correlations which correspond to the diagonal of this figure. There are also some highly correlated features and lower. Also, we tested different combinations of the thresholds, and the number of features selected really depends on these thresholds. Below, I will present several various combinations with nearly the same number of features selected. We consider five-fold reduction of the number of features. So, from 200 features, we reduce the rate to about 40. These are the selected features. The green circles are the features that were dismissed. We see that some physical values, for example, x and y and y components of the magnetic field were dismissed completely, which corresponds to physical notions regarding the importance of various variables. And different other variables, we have some sparse points, taken the number and the position of this point, and also the parameters of the as a result of selection of significant features, optimal sets were selected, and the selected features are consistent with the physical notions of the physical problem, both on the physical values selected and on the temporal variation which physical value. Regarding the index forecasting, the results, statistical results of the forecasting, this is the green line, are just a little worse than the forecast made with the full array. So by now we didn't succeed in improving the result of the forecast, but we reduced the number of input features fivefold without significantly worsening the results. So that is all. Thank you very much.
Only one question, because also use all times. This one short.
Short question.
Short
question. How do you know that you found the optimal set of features? You do not prove. It looks like you use a local algorithm for finding features. Just take one and then take only relevant features.
There are two aspects. Thank you for the question. There are two aspects regarding this problem. One is relevance of the selected features from the point of view of physics. We use just an adaptive algorithm which knows nothing of the physical processes, and if it selected some strange features from the point of view of physics, then we should make a conclusion that something is completely wrong. Happily, this is not the case, and the features that were selected, our colleagues, physicists, which are also co-authors of this paper, regard that the selected features are justified from the physical point of view.
It's good.
The other aspect is just from the point of view of prediction. Are the features really optimal for prediction, or another set of the same size might be better? By now, we tested several sets, and the best one was those selected by this algorithm. Of course, this is not, there is no guarantee that there is no better set. Of course, we can use, say, a wrapper feature selection method, which is extremely computationally expensive, but it will definitely provide the best combination of the parameters. Regarding this problem, we tested now another study, and the features selected by just the wrapper method were very similar to that. However, a little different
but they seem somewhat noisy, because the data array itself is not very clean. It contains a significant amount of noise, and the selection method based on statistics, of course, it is very sensitive. So by now we think that both approaches have right, they are right for life, and we just should compare the results.
Okay, thank you very much. Because my question for you, we have another speech. Probably you present it after that. No break. Okay. Please,
As you say,
because for one, I ask probably one by one. Please.
okay. Please.
But remember about the requirements. If you need.
Know that Professor made a document that some people also like to look how confidence online because it is translated.
Okay. Don't broke our. Okay, please. Second one, just a minute, is my glass. Second one, Pertsau and Lukashevich, compression of convolution member on the configuration. Please.
So, to everyone,
But remember about 40 minutes.
I would like to introduce our experience in compressing convolution neural networks. It's a new topic, it's a new area for us, so it was quite interesting to see, to analyze the results. So,
Let's go.
там было, он будет So it's quite important. Every year we get new models in convolutional neural networks. Some of them introduced in this slide, but every model, number of parameters in the model became greater, so bigger, and so on. At the same time, obviously, we have small devices such as AI thinker. It's small board like Irina is just 500 kilobytes static RAM. So big number of parameters for this device become not good. Quantization is what is quantization for training model often in float point mode. So quantization is convert from float point to integer or half-float value. In TensorFlow that we used, there are two different approaches for quantization. It's post-training and one-to-pair training. In post-training, when you train the model in traditional float point, and then just convert it to integer value and save the block. In one-to-pair training, you before training, you convert it to another type, for example, half-float or integrated integer value, and train it with this integer or half-float. So, in our experience, we work with 8-bit integer value. It's just begin with with our experiments. So we met with traditional data sets, data sets like NIST and CFA. It's examples of NIST and CFA. Also, we make training, validation, and test sets, 70, 20, and 10% respectively. To validate the results, we use collapse and parameters GPU and CPU, the epoch counts is 15, batch size 125, and loss function was the variable percent. The convolution neural network architecture on the slide. It's rather small and easy model with just two convolution layers, two multicollinearity, and one button for power and dense layers. In experience, we work with quantization full model. All elements was quantized in post-training mode and underwear mode. And lenses just convolution layers, just dense layers, convolution dense, that's all. So, in the default model, this neural networks is the full area for points, traditional version. Loss function and accuracy and predict the slide, and the result. After quantization, I should introduce show the default model is this is without quantization, without any optimization. Quant model is post-training, so we receive the default model, quantity, save, and back. And we show result. So the result is not good, 83%. Quant-aware training, quant-aware is dense and convolution, but 3D. So it's after training in quant mode. So, the result was very interesting, as you can see, accuracy more than in original default model. And to check, to validate results, use CFA and fashion list. The result was the same. With this network, after quantization, result was webcam. So compression as conclusion. So compression ratio of the model, we say all these models, analyze result. So that was near 4 times according with the rule from float to 8-bit integer value, but almost the same size in memory. It depends with terms of all specifics. And compressing the model doesn't affect its accuracy. See, maybe sometimes it's more good, but 61, 65%. I think now it's the same. Maybe better, not me. So, thank you for your attention.
Concerning the real-world problem you will solve, and the platform where you use your compressed models. You understand?
Okay. The problem is second slide. Number of parameters bigger and bigger. But at the same time, they appear some new devices like AI thinker, for example. It's more like Arduino in format of Arduino, but AI thinker. I don't know.
CPU precision. How many bits?
It works it's low points, but the size of memory there just 500 kilobytes. So it's very small. Well, so when we use traditional neural network with hundreds of millions of parameters, so it's very big to store there. So we try to compress it and use it. But nowadays we test it in Google Colab because I don't have this code, so it's just experiment. In the future, will be AI thinker, Raspberry, Arduino, maybe something else.
Why do you don't use tiny library? Tiny ML library.
No, I don't know what this was.
There is library like Zhou, for example. You can use some algorithm real fast.
Okay, I analyze this library. Okay, thank you.
Thank you for your presentation. I have a question about maybe you think some architecture reconstruction, not only by types, but maybe change in some algorithm to change count mirrors, maybe change count layers.
In real life, in real production, I think yes, it's important. So you need to optimize the model according to your task, with your neural network. And I think as you can see, NIST and CFAR, for NIST, it was very good result. For CFAR, not good, just 65%. But it was interesting to see the same model for different data sets, how it influenced, how it changed. So,
Okay, thank you. Thank you very much for speaking. One, please. Alexander, question please, you prepare.
I know agenda. Also, we are confident to do from the very beginning, and this is just another kind. This is an attempt to formulate some methodology for solving high-dimensional multi-parameter inverse problems of direct measurements. It's kind of a construction set for children when we combine some more well-known approaches, some less well-known approaches to fit into just some checklist that could be used for solution of such quite complex tasks. So a few words about inverse problems at first glance. We try to determine some system parameters from the observed data describing the system state. These are the problems of indirect measurements. Nowadays, nearly all experimental science is the science of indirect measurements. If we learn how to efficiently solve the inverse problems with such properties, it would be very important for the natural sciences. Solving the inverse problem means estimation or approximation of the inverse function. This is the transfer from the observed data to the parameters which we are interested in. And such estimation or approximation are often well performed. Slide doesn't fit into the screen. This slide не помещается полностью в экран. Yes, by machine learning methods, that is what we try to do for such type of problems. The properties of inverse problems are well known. They may be influenced or even incorrect due to instability or non-uniqueness of the solution. They are often nonlinear. They often have high dimension by input. That is what we call just high dimension of those problems. And they may have high dimension by output. They may be multi-parameter inverse problems, and we need to determine not one parameter of the output, but several parameters. So the goal of this study is elaboration of a special methodology for solving high-dimensional multi-parameter inverse problems of direct measurement by machine learning. The grounds are our experience in two main areas, key problem domains, those of exploration in geophysics and of optical spectroscopy by machine learning. Now a few words about general approaches to solution of inverse problems by machine learning. We distinguish two main approaches and one intermediate approach here. We call them model-based approach, experiment-based approach, and also a quasi-model approach. Use of selection of one of these approaches is determined by the utility of a model for solution of a direct problem and also experimental data. The model-based approach requires an adequate model of the direct function. It may be an analytical model or just a result of computational solution of the direct problem. Therefore, the data sets with necessary representativity for machine learning models construction may be obtained relatively inexpensively, and this approach is usually preferred if really a good model is available. However, the obtained solution will be only as adequate as the initial model of the direct function. A good example of exploration geophysics, when we are able to compute the direct problem by finite difference methods, and so it fits within this approach. The experiment-based approach is used when no adequate model of the direct function is available. but we can obtain data sets corresponding inputs and outputs with acceptable representativity in experiment. So within this approach, there is no problem with the relevance of patterns because it's just ensured by the experimental source of the data. But the amount of data really available is often insufficient for adequate model training. Special methods which are suitable working with small amounts of data. An example of suitable problem domain are the problems of optical spectroscopy of liquids. Let's say because we cannot compute the direct problem for liquids, we cannot compute spectra, for example, of multi-component solutions, knowing just the concentration of the components, but we can measure them. So this is just the case for the experiment-based approach. However, what should we do if neither an adequate model nor data sets with acceptable representativity may be obtained in experiment? And we have only a limited amount of experimental data. It seems to be a way out if we use some statistically based or approximation, so-called quasi model of the direct function to generate additional model data. Of course, the obtained solution will be only as adequate as the quasi model, and as this model is not subject area based. In general, there are grounds to expect that it will be a good model to generate data. It's interesting that for about 20 years since this classification was first suggested, we had only just several cases, about 2 or 3, when this quasi-model approach worked really better than the experiment approach. In the case when the amount of data was limited. But several years ago, we found that modern generative neural network models are very effective as quasi models in this case. For example, generative adversarial networks and more effective relational encoders. Mostly, we think so that this is due to the fact that they really can model the distribution of data in the Latin space. So this solves the problem when we add generated data to the experimental data array and train our networks on the combined arrays. The results obtained on independent data sets are better than the results obtained on the experimental data set. So this approach really works. The next point are the types of integration, which we also tested. First of all, this is kinds of cross-validation of some types of data taking, integration of algorithms, assembling of methods, boosting, weighting, staking, others. And also, which is more interesting and specific to our problem, is integration of physical methods. When we perform joint solution of several numerous problems with different input data. For example, with different kinds of spectroscopy or different kinds of geophysical methods. But I should stress that we need to have the same output, the same target parameters. However, machine learning methods are often sensitive to the number of input features, and therefore efficiency of such integration of physical methods needs to be tested in real computation experiments. So we, from one point of view, we bring additional information from concurrent physical methods. But from the other side, we increase several-fold the number of input features with all the consistencies. These are a couple of examples of integration of physical methods. The main conclusion here is that if we try to integrate methods with much different efficiency, the upper diagram, then the integration phase, we see that let us look at the right picture. The absorption spectroscopy provides much lower errors than ground spectroscopy, and joint use of these two types of spectroscopy works worse than the strong method alone. However, if we integrate methods with comparable efficiency, the second example is from the field of exploration in geophysics. Excuse me, the Russian slides, I didn't just succeed to find the English version of it. However, we see that combination of any two methods, and especially of three methods with comparable efficiency when used separately, brings better or even much better results but in respect to their separate use. Now, I should also mention the method of reduction of input dimension. These are quite well-known things. Three main types of feature selection methods, instant methods, wrapper methods, embedded methods, and also feature extraction methods. I will not waste time, these are well-known things. And also, it's interesting to consider methods of reduction of the output dimension. We have a multi-parameter-based program, then we can use either autonomous determination of parameters separately. We build n models, single output models for each parameter. We build separate models. We can use simultaneous determination when we have a single multi-output machine learning model. But this approach rapidly degrades with M and is unusable often even if we have multiple. More interesting, we can use group determination when parameters are combined into groups, and within each group we use simultaneous determination. The success of this method depends on the principle of grouping. If we group together the parameters which are similar to some extent, this approach is successful. If the parameters are completely different, yes, then this approach doesn't work. And the fourth one is sequential determination. If the quality of parameter determination is much different, then it may make sense first to determine the good parameters which are well determined, and then to use their values as additional features. This approach also works sometimes, and it's also interesting to know that simultaneous use of group and sequential determination it never works. So it's completely different. These are completely different approaches to first problem. So now let's move this, and here is our attempt to formulate the methodology. Thus, the zero-stage is planning when we plan either model calculations or experimental measurements, depending on which approaches of the approaches we can use, the model-based approach or the experiment-based quasi-model. Also, we should take into account the security of integration of these methods, because the statement of the first program should provide a determination of the same set of parameters, a model that we can implement. Next stage is obtaining data by calculations of measurements, maximizing the number of patterns, and if possible, generating additional data. Then we should analyze and perform reduction of the output dimension, make initial decision regarding the type of the output parameter grouping, this one, or this one. Then we should evaluate and reduce the input dimension using one of these well-known approaches of feature selection, which may be meaningful or adaptive, or also extraction of the features. Then we should evaluate the necessity of data integration, make the initial decision on the use of cross-validation of some other types of data. The next stage is the evaluation of the arsenal of suitable machine learning methods and evaluating which methods are available for approximation of the inverse function in the specific case. And finally, we should build basic solutions of the inverse problem by individual machine learning methods in autonomous determination modes and based on the data of each physical method set. So these are basic solutions which further will be used as reference solution. We should compare all our subsequent results with these reference solutions obtained separately or separate methods. If possible, at this stage, we should perform the research of optimal parameters of each method. And these are the main stages of the methodology, considering integration of the algorithms, integration of physical methods. So we begin to combine various methods together, and each time we compare the results with the reference ones. Finally, we evaluate the effectiveness of the approaches used, and if necessary, make changes to some of the initial decisions made regarding the approaches, regarding various types of integration, and repeat the work starting from the So the sequence is repeated until the desired result is achieved or until the available resources are exhausted. And also some stages may be omitted depending on the specifics of the task being solved as well as on the railroad. So we hope that this checklist may be used as a starting point by a researcher who is solving an inverse problem of the supply type. And also, if we omit some problem-specific stages, it may also be used during solution of some other problems. Thank you for your attention.
Thank you very much. Question. Sorry. Do you have some questions? As usual.
Okay, I would like to ask you because usually it's important to ask this question. Okay. Can you say us or present us at least one example of the problem you are solving? So what is like input data? What kind of measurements you do, and what based on these measurements you would like to estimate?
Thank you. I mentioned. I just have no slides. I will have to either tell you in a few words, or I can show you afterwards. The two main problem domains are exploration geophysics, when we calculate the direct problem. That is, the problem setting is the following. We need to restore the distribution of some physical property within the Earth's crust, for example, electrical conductivity or the density of the material. If we know this distribution, we can determine if there are some useful fossils, oil or gas or ores or some others. But the only really reliable method is drilling, which is extremely expensive. So there are physically based methods which are based on measurement of some physical fields on the surface of the Earth. And so we have a very large inverse problem. We have a multi-input data set, the measurements of the fields in different points on the surface of the Earth, which also have different frequencies, also different types of fields, and from this large amount of data we need to restore distribution, which also should be parameterized to use a finite number of parameters to describe this distribution, and then to use some interpolation to restore the distribution in the code. Our colleagues from the Geological Perspective University have their algorithms to calculate the direct problem for three types of three types of inverse problems of exploration geophysics: gravimetry, magnetometry, and magnetic horizon. The problem is bad enough to use machine learning methods to solve. We have been working on such problems for about 15 years, till now together with our colleagues. So the results are better than the conventional methods of solving these problems. Afterwards, I will tell you how these problems are usually solved without the other domain is optical spectroscopy. Our colleagues from the physical department of Moscow University obtain unique databases of multi-component solutions, ranging from mixtures of inorganic solutions of inorganic salts to beverages, mineral waters, alcoholic drinks, wines. In general, the problem is the same. We need to determine the concentrations of various components, either of ions in dirty waters or of some components harmful for health in the beverages. The problem cannot be calculated, the direct problem cannot be calculated, so we use machine learning methods to solve this problem.
Short question and short answer, not new and important. Please.
Thank you for your Zhou presentation. Maybe you hear about the trend networks. If you use another long big data set for another task, but very similar, and you maybe this is problem insufficient data, you maybe resolve.
Thank you. You need the transfer learning approach, of course. Just during the latest 2 years, we started checking this approach, but the main problem is the specifics of the tasks which we solve. For example, for geophysics, we can have a general parameterization scheme, calculate quite heavy neural networks to solve the problem, and then test local geophysical structures, some layered structures or portal structures or some others, with a small number of calculated patterns. Now we are testing this approach. It seems that it should work, but there are no final results, so just now I will. Thank you. Yes,
Thank you for very good.
one reason for cooperation with anyone.
Okay, I think we will have time during the next 2 days. Okay.
Thank you.
Next one is I come to Rodchenko and Vadim from the mirror method interpretation in Google. Okay.
And
we have data set from 150 examples, which are divided into training part and testing part. And each sample from this data set using describe some geometric shape of iris flower and contains four main features: sepal length, sepal width, sepal length, and sepal width. And we have actually three classes of classifying these irises. It's very famous data set, very and simple actually. It's very simple. And we use model with very simple structure. Here our approach.
As far as I know, iteration function in box machine is stochastic.
Yes, yes.
And one more remark. In fact, sometimes neural networks are called as a gray box model. If you ask Google, it will explain that I mean.
Okay, thank you for your question. Yes, this Rodchenko machine use this is stochastic model, but here we use this Rodchenko machine in more deterministic way. We change activation function on another. For example, we use non-linear activation function for example, real function and tangents, hyperbolic tangents, and so on. But we found is probabilistic basis. We use probabilistic variant of this, as you can see, as you can solve, yes. But it's not we get not best result.
Okay, I mean, you modify.
Yes, we modify.
Listen,
What do you mean?
give.
I'm not removing
Get.
because remove.
Get. Move. She decided to stop. Understood? Thank you very much. The last guy.
Sorry about, yeah, it is. Okay, it's right. Okay, so the topic of the talk, as you can see, is a visualization and prediction system for floods on lowland rivers. And to start with the scope, I would show the first slide, which actually represents two main features of floods on all rivers. They are very big. The first feature is that, well, you see everything is evolving really slowly. You see some rural citizen which slowly float somewhere in his boat, and it's completely different from, for example, mountain river flows, which have great speed and a lot of, consequences from the wave which comes and crashes everything. In lowland river situation is completely different. No fast changes at all. But the problem you can see on the same slide is covering of really large areas. By the way, in case of PRIP', for example, a river which we are mostly interested in, when you have 1 meter higher water level, you may get about 30 square kilometers of land covered with water, and that obviously brings absolutely different problem. The wave is not a problem, but the high water is staying and covering some, lands which are involved into some technogenic activities, bring a lot of damage. And if we consider such a lowland river system as a model which can allow us to predict this level of damage and the flooding at all, we should take into account a number of parameters from the climate, which I would say obviously is, well, not from the climate in this case, but the first thing to take into account is obviously the terrain. The model of the terrain we want to take into account when getting into the problem and trying to predict which areas of the terrain will be covered by water. That's absolutely obvious. What else we can deal with? Obviously, water level in some measuring points is important, but from the hydrological point of view, we deal with water discharge, which is actually the same. Well, because they measure the discharge of water coming through some well-known cross-section of the river bed. So for each measuring point, for each hydrological pulse, we have strict connection between water level and water discharge. So we can take into account either water levels or discharge in the specific points of the riverbed or of the watercourse, let's say, and finally some climate parameters like precipitation, the accumulated precipitation, like rainfalls. Then the snow cover, which is substantial in case of lowland rivers with mostly snow feeding. Well, it may be not so important in some areas which see snow one time in 50 years, but in case of Belarus, for example, and in case of Europe and Asia and a lot of other territories which have not so warm climate, it's really important, but because it changes flooding situation a lot. And finally, the air temperature, which obviously is a very important parameter, which we will look later a little bit. So, what we can get from this? We have height of the water, or water discharge, and after that, we can draw the contour of the flood zone. And if speaking about the prediction based on the same parameters I already named, we can use the current situation of the water level and the set of the spoken above line parameters to have the next predicted, now not measured, but predicted discharge value or in the water level. And then by a typical time series prediction with a sliding window, you get tomorrow, day after tomorrow, and so on for typical horizon of 7 days, which is typical technology. And obviously, for each of them, you calculate the flood zone and get the situation in the next phase related to the river flow. Then, when implementing this model into a real set of models, we had a requirement of highly modular system with isolated subsystems that would allow us to substitute any part of the system with absolutely different model, either for different area, well, taking into account different terrain, for example, or for some other reasons, like searching a different approach to deal with one of the parts. So we have three systems: a prediction subsystem you have seen on the previous slide, which takes discharge and maybe some climate of parameter like which we call data, and try to guess the next value of the discharge on the same control point. Then flood zone calculation subsystem, which actually draws and does say calculates the polygons of the high water covering the terrain, and visualization and calculation of risks. Both flood zone calculation subsystem and data visualization and interpretation subsystem use geographical map data. Actually, the OpenStreetMap is still a good source for this. And, well, if speaking about the steps we need to take into account of doing demand for prediction of the final result, first we need to have some estimate of the snow power and tell a little bit about it. Then we have to predict the time series of water level or water discharge in several control points by the same approach actually. Then after that we can build the flood area polygon, and then after analyzing the landscape fragments, we can estimate the potential damage of this flood. Why the talk, which is highly related to topology, is presented here, we used neural networks for predictions of system. And taking into account the requirement of isolation, we actually used 4 separate neural networks. The predicting neural networks, actually 3 of them were used to deal with different types of situations, because it's just brought us better results, and the additional correcting artificial neural network for satellite data to estimate the water stored in the snow cover was used. So, a little bit more about this additional supplementary neural network. When we want to guess the water equivalent of the snow cover, because well, in the mountains, it will give us water once we will have the positive temperature. The most technologically assessed approach
is using satellite data, because we have the empirical equation presented by Chang some time ago, not recently, by the way, maybe in the 80s, if I'm not mistaken, which uses some frequencies of radio wave scanning to guess the amount of water in the snow cover. It's rather a simple situation when you have some atmospheric radiation, then it's reflected from the Earth's surface and acquired by the scanner of the satellite, and so-called SSMI scanner. Then we can have some attenuation of the Earth surface radiation by the snow cover, and dealing with the specific frequency bands, we can guess the amount of water in the snow. But there is a problem. There is a rather good empirical equation, but the problem is it's rather good because it's the only one we have. But if comparing with manual measurements, it's not very. It's well known for rather large errors emerging in some situations. Well, and you see the amount of frequencies which are typically measured, and only 2 of them are used in this equation. But obviously, other frequency ranges are also influencing the situation. Just the authors of this empirical regression didn't find how to take them into account. So we used typical neural network approach to get some improvement over the original channel equation. By the way, that was absolutely practical task, so we used absolute classic, the classical persistron with, well, you see some architecture here. One intermediate layer, carefully determined as an actuation function, well, just absolute classic variant. What's good here is and we had to use a lot of real data from the large territories to train it, and actually we used the data gathered over the Russian Federation for that. Well, it's much larger than ours, and that brings us more accurate correction. Which was then, in our case, as we were oriented to recruit report, it was applied, and we got actually a better coincidence with the manual measurements data. By the way, I would say that these SSMI data are not very accurate. Actually, the cell size is 25 square meters. That's why we needed larger territories to train it. I will not stay on this. Oh, sorry. Yeah. Here it is. A little bit more about predicting neural networks. We initially planned to use 2 of them. Well, because we are. Oh, sorry. I mean, no, okay. Because we have actually 2 types of spring floods, which are obviously related to the stored water in the snow cover. The one is so-called high spring flood, the other one is minor spring flood, and it's highly dependent. It is highly dependent on the temperature when the average daily water flows are obviously recorded in hydrological laws. We use this water discharge as one source, and the total volumes of water accumulated in the snow cover on the study catchment area is used as another layer when we know that we have a high spring flood. Then the artificial neural network number 3 for minor floods is used for the cases when the soil has initially significantly absorbed water from the snow. Well, you know, some winters are actually winters only by name. And if the snow will be melted, or if you have not too much of it, then it will just have no significant dependence or significant influence on the water flow in the area. For this case, we use the second time neural network, and the good point is we have a really simple criteria to guess based on the daily temperature with a specific period of time. So we already know with 100 or 99 or 100% probability that we will have either high spring flood or low or minor flood. And actually, we initially had only 2 neural networks trained separately, but suddenly we had to get additional neural network for high spring floods in case of the broken satellite measurement system. Because, well, we just met a situation when SSMI scanner was broken and we had high spring flood, we had no satellite data, and we still had to address the situation somehow. That's why we have the second neural network of high spring floods, which avoids using satellite data at all. Still provides a better result than using one for minor floods. Then, what about the architecture? Well, it's a typical medium. Well, it's really similar architecture to shown here, only 2 inputs in case of neural network 1 and 1 input in case of second and third. Typical multicollinear strong sliding window of 7 and 8 days. The window size was chosen empirically. And obviously the time series which we have viewed are looking like this, and you see the peak when we really have to predict the water level. And obviously we had some experiment with the size of the layer to choose the better one. You see the errors are rather low, and we get, from the meteorological point of view, we get rather good results for 7 or even 10 days. Once again, not from mathematics maybe, but from the meteorological point of view, it's good enough. So we can stay with the classic neural networks without any experiments in this case. And the problem of visualization of Platon population subsystem is rather curious. First of all, normally we have a train model, and the typical approach is to use flat surface which covers it, and intercept of the surface of the is equal to the water level. Actually, it brings really 2 problems. One is computational problematic, when we need not as much details, and the other one it gives us some isolated areas which shouldn't appear if we simulate flooding by geometric approach. But in some more sophisticated. So we used combination of intersecting 4-dimensional surfaces and a raster algorithm which spreads water over the surface. Actually, it's a really well-known raster algorithm. The same, for example, which is used for tracing cyclic boards. I will not stay on it for a long time. I will just say that if we draw a current situation, we have some control points, kind of hydropods measuring the water discharge of these cross sections of the river. And if we deal with prediction, we need neural network-based prediction for each of these points based on what I will already describe based on which parameters they are. So it allows us to exclude isolated areas which are not covered by water in real life. And if we have a small fragment of the water course, it's okay. If we have the river system with several water courses, which we normally do in case of any large river bed, then we need to use additional tools to additional approach to combine water levels from several water courses. Well, I will not stay on it too much. Also, well, it's a rather large separate topic. We use solar automata to combine water courses. And actually, to calculate the same raster style spreading over the surface based on several water courses. Obviously, it's referenced in the references section of aspects. And coming to an end of the talk, well, if we need to guess some, potential damage, we need to distinguish landscape types like field, urban area, and so on. And based on this, we can use some probability-based equations for the damage, for the risk of damage, based on duration of flying and based on depth. And the final visualization brings us the flood, actually the flood zone, you see it here, with silver coloring. It shows actually the level of risk in any parts of the model plane. And probably, I think that, yes, I'm absolutely accurate in timing. Probably that's actually the end of the presented research system. And thank you for your attention. If there are any questions, I will be glad to answer.
Thank you for your impressive speech. Please, have any some questions?
At satellite, what you are using?
Good question. We need to guess the level of water stored in the snow, because when snow will melt, this water will go into the river flow and highly influence the spring flood. And that's we take the radio frequency method, well, microwave data gathered by satellite. It's an international project with publicly available data. That's why we can easily use it without any projects and without any problems, if they are available. And there is an empirical approach which we use as an initial idea. The empirical approach to guess the amount of water in the snow cover based on the radio frequency measurements from the city. But we use the neural networks because, well, Zhao gave us better results after correcting. Well, neural network was, let me move here. That's not nothing bad with the theory, but it uses only 2 frequency bands, and actually the satellite gives us 6 of them. So we have neural network as a workaround to take into account by the frequency range, and by the way, getting more accurate response, which, well, was checked. The accuracy actually was checked on the basis of the data of Krasnoproshin to make sure that we definitely get that result. It's not presented here in detail actually. Well, one of the references sources has much more details on this. Thank you for your question.
Yes. If
I understood correctly, you have two networks.
Oh, we have four networks.
And separate data.
Oh, yes.
You have one network for strong plots and the other one from.
Initially, we wanted to have one network for strong floods, which which are highly influenced by snow, and another network for weak floods, which are practically undergo no influence. The reason for having two of them separately is because, well, we have really strong criteria to guess whether we will have strong flood or weak flood. Actually, the climate, the temperature in specific time provides us really adequate information of what should be late.
So this was actually my question. How do you solve which of the two networks you should use?
Great question. The strong point of the climate relation of the flooding, of the river flooding, is that we already have information about whether we are waiting. Actually, it depends on the temperature in a specific month. So we know this already. That's why we can choose the proper network without trying to get some combined option able to predict both variants. We already know.
What is the sense of this condition?
Which one? That's water equivalent of the snow cover.
No sense in this condition. Because we just compare with the positive or negative difference.
Oh, no. Please don't pay attention for this snow presence. It means that if water equivalent of snow cover is positive, it means that there is
I see
yes.
Z got 0.
Yes.
It will be bigger if you multiply by 1,000, 1 million, this value in parentheses.
On the side.
It's a quantitative value. It's not, it's written here that we just show it is bigger than 0. It's obviously bigger than 0 because we cannot have a negative amount of water and snow. We have definitely positive values. And if you see, good question. Here we represent the actual values of water snow equivalent in grayscale. So, you can guess it as an arbitrary unit, but actually it's used in methodology for, I think that's since 80s. So it's their typical variable used for such tasks. For us, it was looking a little bit strange as well.
What is the resolution of your satellite data?
Oh, 25 square kilometers. 25 square kilometers. It's really low resolution. You see the territory of Belarus covered with these cells, and each cell is actually one measurement. So the resolution is really low.
Okay.
The only problem is that the alternative is manual measurements of the cape of the snow, which has a much lower resolution than this satellite, because, well, we have maybe 7 points where we measure snow 8 manually in Belarus, and here we have much more cells than 7.
Okay. But you are assuming that snow is the same everywhere. It's not true.
It's obviously a generalization, but its generalization is much better than mine.
Okay. Thank you for everybody for participating. I repeat, every of them should be a presentation for this one.
Learn computation.